So I wanted to take a lesson here and go through binomial expansion. You guys have done bits and pieces of it before, but it's neat to look at with some more complicated examples, especially since we've been doing some pattern stuff. So the whole idea is, if I ask you to do a plus a b quantity squared, we'd write this out like this. We'd double distribute everything, and we can safely assume this is what would happen. So if we now ratchet that up to a plus b quantity cubed, we would have, 3 parentheses of the a plus b. Well, if we've already done the first two, we can just take that down and then you only have to do one more. So I'll save you guys all the work with the double distributing, because we're going to be looking at patterns with this anyway. But this would come out to be this right here. So then same idea if you wanted to do an a plus b to the fourth. You'd have 4 sets of parentheses. That's a whole lot of double distributing to do. Since we've already done it to the third, you would take this entire thing here and just add another a plus b on there. So you'd have 4 terms times 2 terms should give you 8 total terms, and then they're going to combine together. Just to save some time and you guys the work, this is what should happen. So you may be able to see some patterns or remember when you looked at it in your other classes. But basically, there's a reason I could do those quickly without having to, look at everything and do all the double distributing. So the first term is always going to be an a squared or an a cubed or an a to the fourth. So if we wanted to do this to the 10th power, first term is always a to the 10th. Last term, b to the fourth, b to the third, b squared. Again, same idea as that. It's all the stuff in the middle that we need to figure out. So if you'll notice, look at the coefficients. 1, 2, and 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. Okay, those are special numbers. They come from Pascal's triangle and also from combinations we'll look at. And then the other thing is the A's will count down. So 2 A's, 1 A, 0 A's. 3, 2, 1, 0. 4, 3, 2, 1, 0. Okay, B's go backwards. So there's no B's, 1 B, 2 B's, 0 B's, B to the first, B squared, B cubed, 0 B's, B to the first, squared, third, fourth. So really all I'm doing for that is I'm using Pascal's triangle here. There's the 1, 2, 1. There's the 1, 3, 3, 1. The 1, 4, 6, 4, 1 that I used previously. I'm using those to get the coefficients, and then I'm just counting down with A's, and I'm counting up with B's. So here's a little summary, kind of everything we just looked at. Coefficients come from the triangle, so if you want to do it to the 8th power, you would go to the 8th row. Okay, and you know it's the 8th row because of counting numbers are on the second diagonal. So when I did that to the 4th, I just know these numbers. 1, 4, 6, 4, 1. Variables must always add to the power. So if we go back and look at this, 4 plus 0 is 4, 3 plus 1 is 4, 2 plus 2 is 4, 1 plus 3 is 4, 4 plus 0 is 4. 1 starts with n, the other starts at 0. Like we said, A's count down, B's count up, and the last little piece there. Okay, so this is actually from the Algebra 2 book. If you wanted to do an a plus b to the 6th power, so you could sit there and you could do a whole lot of double distributing. It'd take you, 5 times if you did actually all of them out. So I know it's to the 6th power. So automatically I'm going to go to the 6th row. I'm going to grab all these coefficients. 1, 6, 15, 20, 15, 6, 1. You know the first term is going to be a to the 6th. you know the last term's b to the 6th. So 1a to the 6th plus 6 a's count down, so it's now 5 a's. The b's kick in at 1 because these have to sum to 6. So then 15 a's count down, we're now at 4. B counts up to 2. 4 plus 2 gets us to 6. Okay, 20 a cubed, b cubed. Now 15 a squared, b to the 4th. 6 a to the 1st, b to the 5th. And finally 1, you don't need the a to the 0 because that's just a 1. 1b to the 6th. So if I ask you to do a plus b to the 7th, you just go to the 7th row here. There's all your coefficients. A's would start at 7. They would count down to 0. B's would start at 0. They would count up to 7. And then make sure you have your plus signs separating them. Okay? Now, those are pretty easy if they stay at a plus b's or x plus y's. But what if you have something like this? So if I ask you to fully double distribute or expand that, you could write this out like this. You could double distribute these. You could take that product and then double distribute it into that. But there is a shortcut we can use. So it's to the 3rd power. I'm just going to pretend this is a plus b cubed. Okay, and you guys may have done some examples like this, but it's a really good practice for us. So 3rd row is going to be this. So I'm just going to kind of start with what I call a skeleton. Okay, so that's what a basic a plus b cubed should be. Now, the a is a 2x, and the b is a positive 3y. So we're just going to go do a substitution now. And make sure your parentheses are in the right places and you distribute your exponents correctly. Certainly don't try and do this all at once. It's real easy to make a mistake. And once you get this all set up, all you got to do is go simplify it. So quantity 2x cubed is 8x cubed, because that 3's got to come into both of those. Same idea with this squared here. 3 cubed we know is 27. So it may take a couple steps to go ahead and simplify all of these. Now, when you have things that aren't just a's plus b's, your numbers are going to change. So you're not just going to have 1, 3, 3, 1. Okay, so don't be worried about that because we had to take care of the 2 and the 3. But your your variable should still be the same. 3x's, 2x's, 1x, no x's. No y's, 1y, y squared, y cubed. Okay, so the variable should still be taken care of unless it's something, like 2x plus 7 quantity cubed. Then everywhere there wouldn't be any y's in there, there'd just be 7's. Okay, so if you build the skeleton and then you do some substitutions, it's not too bad. You just got to take a couple steps with it. Okay, brief little detour here. Looking at combinations again. So permutations, combinations. Obviously, the big difference is combination. The order doesn't matter. You're just selecting people. They're all doing the same role. So if you want to say, how many groups of 4 can I make out of 29 students? Everyone in the group has the same responsibility. It doesn't matter where they sit. Okay, they're doing the same thing. The order they're selected doesn't matter. So out of 29, we want to choose 4. Well, actually, let's give you the formula again in case you haven't used it in a while. So we go n factorial on the top. On the bottom, we go n minus r factorial. And then to make it a combination, we divide by that extra r factorial piece. So in this case, if we get 29, choose 4. So you guys usually done these in your calculators, but it's good to see just where all this math comes from again. So everything under a 25 is going to cancel. And then your 4 factorial is 24. So when you guys do these in your calculators, this is really what's happening. So you guys have always said 29 math over to probability combination 4. Okay, so there's 23,750 ways, 51 ways you can do this. Okay, in part 2, we'll keep going with how these combinations will help us in binomial expansion.